So a little about me. I'm fairly old, as they say, which is why they've made me a consultant. And I worked in the aerospace industry for quite some time. I worked on Hawk trainer, which some of you might know as T-45 in America. I worked on the Harrier jump jets, or Aviate-B as it became when we sold it to America. After that, I moved into Airbus, worked on Airbus Wing, A320, A350, A330. And since I left aerospace, I've actually mostly been working in the car industry all over the world, but I've kept my hand in. I've been working with several engine manufacturers, turbine blade manufacturers, and just a couple of airframe manufacturers over the last 10 years. So let's move on. We don't have a huge amount of time. When we say aerospace industry, and if you're not from the aerospace industry, please don't log off. I think you might find some of this stuff interesting anyway. But what we're talking about is aircraft assembly, airframe manufacture, engine manufacture, and the maintenance and refurbishment of all of those things. Okay. Now, we've also got experience of working with aircraft systems manufacture, radars, in-flight systems, and all of this lot, but most of our experience is in those areas. And I say we want to consider the maintenance and refurbishment because in every case, you know, we have to keep all this data for the entire life of the vehicle plus. Okay, let's move on. The aerospace industry, it is uniquely regulated. You know, the amount of paperwork involved in getting an aircraft into the air is probably double the weight of the aircraft by the time it actually takes to the air. And that does leave you with a fair amount of inertia and lack of flexibility in implementing new systems, especially digital ones. Okay. And this is coupled, of course, with a requirement that data is retained in the long term. You know, we've got to consider how we hang on to data over 30 to 40 years. Yeah. And of course, we've got low production rates. Certainly, you know, we say high production rates in aerospace, so we mean like one a week, don't we? You know, in the car industry, of course, you're talking one every 90 seconds. So this has traditionally been seen as a reason for not doing statistical methods, but actually there's a lot you can do, and we'll have a look at some of the ideas there. One of the big changes I've seen over the last 20 years, certainly, is the increasing length of the supply chain. When I first started, all the parts were made in-house, all the parts were assembled in-house, and then you flew an aircraft out of the runway that you had just outside of the A shed. That's really changed. I mean, British Aerospace now pretty much is a final assembly shop. They don't seem to make components to the same extent, and the length of the supply chain is getting longer and longer. So managing those suppliers and the quality of the parts that they produce has become a much bigger part of the job. And of course, traditionally, you've had very large structures that were difficult to measure. Okay, but we've got new measuring devices. You know, we've got big laser scans. We've got the opportunity on the shop floor to connect directly to gauges and to feed all of that quality data straight back onto the shop floor. I mean, I really wish I'd had that when I was younger. You know, we used to have to measure everything by hand and write it on pieces of paper. And you've got much greater access to all the other parameters. I've called it in-process measurement. So this is where, for instance, you can stick a dimensional probe into a machine tool, but also we've got much greater access than we ever used to have to the parameters inside that machine controller. So we know under what conditions we're producing, and we can correlate that to the quality we're getting. Okay, and that brings me onto the analysis tools. Again, multi-gigabyte databases are no longer a problem. I remember having a IT project rejected once because we estimated the database size to be up to 1 megabyte, and nobody could actually give me 1 megabyte of hard disk space on the company's computers. Now, you'd laugh at that. And if someone asks for 4 or 5 terabytes, they might get that sort of problem. So we can do a much more in-depth analysis these days, and we can do it much more quickly. Okay, let's talk about traceability. And this is gathering the data, really. I said gathering internal data, then collecting data from our suppliers and external sources. Now, they should be the same, but there's some special considerations with the supplier stuff. How do we validate that data? Once we've validated and collected all that data, how do we, I call it consolidate and integrate. How do we turn all those apples, pears, and bananas into the same thing so we can actually do some decent analysis? And then I'll talk about some concepts we've been applying on storage and data dissemination. Okay, I shall move on. We've got a number of considerations when we're gathering data internally. We are very keen these days to reduce manual data collection. One of the areas where we still have issues is optical character recognition and actually gathering data from forms that people have filled in that we've scanned. It's still very easy to mistake a 5 for an S. Okay, and once you move outside of, shall we say, the simple European character set into other more complex non-European character sets, it becomes even more difficult. So we really like to reduce manual data collection. There's a lot of techniques we've got for doing that now. A lot of shop floor tablets and data collect equipment. Okay. The other challenge is how do we compare all the different data types? Talk about that in a minute. And then it's very useful these days to be able to connect directly into your MES or your ERP. Unfortunately, things such as SAP are actually incredibly flexible in the way they're configured, and therefore we need to be very flexible in the way that we can extract that data. Now, I've put the next one is how do we stop people doing what I call a manual edit or a piano playing? Now, I've put those two separately. When I say manual edit, I mean somebody who's edited the data before they've put it into the central database. Playing the piano is someone who says, I don't like that report. I'll go into the database and I'll actually edit the numbers in there so they don't match the original report. And then I'll have a conforming part. And you'd be surprised how often it happens, especially with supplier parts. So how do we prevent that? And having put in some things to prevent it, if somebody does try it on, how do we detect it and create an event or an alarm if that does happen? And then one big issue in aerospace, how do we track remeasures of the same part? These are big things. We can't afford to scrap stuff. So we're going to rework it. That means remeasuring it maybe 3 or 4 times before it passes. How do we track all that, but still use the final condition as our delivery report? Okay. Now, there's a number of solutions. We have we've been working towards having very flexible data loading services. We've been working on what we call a background evaluation service that does all the comparison of the different data types in an almost invisible manner. Okay, that gives us the opportunity to have a complex analysis engine, but at the same time, gives us the opportunity to connect to a lot of these new BI tools that are coming along, the Tableaus, the Power BIs, the Sync Fusions. Now, all of those tools are actually fairly dumb. They can't do three-dimensional maths. They can't relate the measurements you've taken directly to the CAD model. And so we want to do a lot of that in the background before we feed that data to the BI tool, okay? And then something else we've been working on recently is integrating quality measurements and the MES with the RFID tags and the tracking systems that are getting put into a lot of these major components now. We've even been investigating, can we on final delivery push documentation and actual dimensional information onto the RFID tags that stay with the aircraft through its life, and can that be used by the maintenance crews? So we're playing with a lot of this new stuff, okay? Let's have a look here at how our internal data flow would go, considering some of those things that I've discussed before. Now then, I do apologize, by the way, I've got a bit of a cough and I haven't got this COVID virus, but now, of course, is not the time to go to my doctors with a cough because the implication will be obvious. So over here, we've got a load of inputs. Now, I've just put 3. There could be a ton of different inputs coming in here. Now, the trick is to have a single data loading service that can handle any type of data. Okay. And not only any type of data, but has the flexibility that if a new type of data comes along, you don't have to spend a week programming some sort of translator for it. You can just almost plug it in, write some rules for how that data is to be passed, and then get it to work. Okay, all of these things, everything these days produces some sort of data file. Okay, it could be a DMIS, it could be the DFQ standard, it could be an Excel spreadsheet, a text file. We don't care. And down in the bottom here, I've put some new ideas that we've been working on. How do we connect up to the environmental system? How do we connect up to the MES? How do we look at data directly from NC controllers? And as ATS, we've got a team working to produce what we call an ATS bus that can connect to all of these items and serve up the data from any system in a logical fashion. Okay, what we're finding is that a lot of companies, they've got they're not new companies. They've got a mixture of older controllers and newer controllers, older parts of their MES and newer parts. And often these have very different ways in which you have to extract the information. So say we've built this bus, which is a generic data gathering tool from any source of these process devices. All of this lot goes through, in our case, we like to put it through a central data loading service. Of course, we like to think you can distribute these as you see fit, but we find it works best if you've got a central data loading service. When your files come in, first thing is let's validate those files. Once we know it's a valid file, we can parse the contents. That is, we can rip the file to pieces and find the bits of information that we need. And then, of course, we can validate that data before we consider putting it in the database. And it may be necessary to actually reach out into the MES or the controller and do a further validation of that data. Okay, now then, you notice this on the end. For us, we have a central quality database of what I call raw data. Okay. Now, if I'm an engineer, I'm going to love this. This is what I want. I want the raw data. But if I'm a manager, or if I just want the pass-fail information of a part, what I'm going to do is run this raw data through a results service. That service is going to apply the rules, evaluate the data, and then update reports, and then push the evaluated data into what we call a results database. Okay, I'll talk about this concept a bit on the next slide, but the whole idea is that for the most part, managers, team leaders are looking at the results database. Did it pass? What's our pass rate? These are fairly simple questions that BI tools can answer. But I've still got my raw data back here. So why do we have this two database concept? Well, if you think, if I measure something on a CMM, it's actually going to tell me the XYZ position of something and probably the diameter of a hole. It may tell me the flatness of a plane. But it may well be that this CMM has measured, say in a pocket on a rib, it will have measured the position or the flatness on two sides of a pocket. But of course, my functional requirement is for the pocket to be a certain size. The distance across the pocket, or the area of the pocket, or the flatness of the plane, or the parallelism between the opposite faces. Now the CMM probably won't tell me that, but I can take the central quality database, I can do complex 3D calculations on all of that data in order to evaluate it and produce the results that I want, okay? So in effect, as well, I also should mention, of course, in my quality database, my raw data, I have a direct link back to the original data file that was loaded, and from that data file, I've got all the trace fields from the data file in my raw database. I can go back and look at the operator's name, the date, the time, all the equipment tags that I've decided to collect. So we're finding, however, having all the results in a single common currency in a separate database gives me rapid access to the information I require, whilst at the same time having the traceability and the ability to recalculate at a later date if it's required. Okay, I'll move on, but this is a concept we're really pushing at the moment. Let's talk about suppliers. If you've got a supplier, okay, you've got a few considerations. The big one is, let's face it, most of us live on fairly secure sites behind a very strong firewall because the data and the things we're dealing with are important and are in some cases secret. Okay, so how do we get the data from a supplier into our system, okay, without opening up a back door for that supplier to actually attack our system? Okay, now, not only have we got to get through the firewall, let's grab that raw data. Yeah, I can quote a number of examples where suppliers have been sending in Excel spreadsheets or text files that have been, shall I say, adjusted in their favor. It's not uncommon for suppliers to make sure that things pass quality. So it's always best to grab the raw data direct from their measuring equipment if you can, okay? And of course, you should log all the upload times, who's uploading from where, and all the rest. I think that goes without saying. But you've got to remember, each of your suppliers is likely to have a different format for their exports. Now, there are several international standards. There's DMIS, There's DFQ, there's the QIS standard that's coming along. Now, our experience is that these are, yes, standards, but if you look at the DMIS file from a metrologique system compared to a hexagon system, compared to a Wenzel system, the way they structure their DMIS output is actually quite different. And so you need to have a very flexible data loading service that can handle that sort of variability in the data file formats. Okay. Now, of course, we've worked with one company over in Europe, and their standard terms and conditions are quite strict, and it simply says you will provide the data in this format, which is actually their version of the DMIS standard. And again, that if you can do it and get it into that contract is a big benefit because it makes everything more simple. But again, you've got the choice. Either have a very flexible data loading service or a very tight contract. And one thing we also try to suggest when we talk to OEMs is that they get repeatability studies from their suppliers. We are constantly surprised that if you were to take 5 parts, measure each of them 3 times with a couple of different operators and run a repeatability study, and dare I say it, in the aerospace industry, it's worse than the car industry. The amount of variation we see in the measuring process is sometimes quite frightening. So we always suggest that suppliers have to submit a validated repeatability study before they're allowed to send data in. Okay. Now, what is the way we are currently operating when we load data? Obviously, the supplier measures, they get some sort of file. On their site, we have a little utility that's going to encrypt and zip up those data files. At the same time, we're going to apply an end-to-end encryption tag as part of the encryption process. That's great because we know where the data's come from, and we're the only ones who can decrypt it because we've got the decryption tag on our side. Those files are reasonably safe to push through your firewall. They're encrypted, they're zipped up, they've got an end-to-end tag. But we don't push them straight into the database or onto the data loading service. We push them to a separate secure FTP server. And we decrypt and unzip those files there. We would do some basic validation there. And of course, we'd run a virus scan on everything. And then we push that data into our data loading service. And you may decide to have 2 data loading services running in parallel, one for your supplier data, one for your internal. You may even decide to push this data into entirely separate databases just to keep that security. Okay. So I talked about validation several times. Validation, it's critical. You've got to establish the source of your data. As we said, please establish that your data is repeatable. If they measure the same part 3 times, will we get the same result or will we get half a millimeter difference? You know? And I have seen that. I've talked here about veracity and legitimacy. Well, the repeatability and the veracity in a sense are similar. By veracity, I mean, does the measurement reflect accurately the component that was measured? Was it measured in a good way? Was the thing clamped properly? Do they have a good way of ensuring the data reflects what it really is? Okay, do they have good measurement strategies? The legitimacy of the data is slightly different. That's, was this an approved operator who did the measurement? Did he do it on some equipment that was within calibration period? Yeah. Does it come from a reliable source and is legitimate? Okay. Now you can check all of these things, and it's vital these days to do that automatically and to have some form of automatic alarming or eventing if a breach occurs. Now, I've got two boxes over here on the right because you've got two primary times when you can actually do your validation. When you get a file, you can check its naming, its location, its formatting, its country encoding. You can rip bits out. You can look for telltale signs that it might have been altered. Of course, you will put trace fields inside a file, you know, the operator ID, the machine code, maybe a supplier secret code, and you can track and trace these fields that are inside the data. I've already talked about having an end-to-end encryption key for encrypting and decrypting the data, and that should of course be unique to each data source. Now I realize that certain governments are not happy with certain levels of encryption. And we have encountered that before, where we've been blocked because we've encrypted data to too high a level. So you've got to work within the regulatory systems allowed by the local government, whilst at the same time ensuring the maximum level of encryption that you can. Okay. Typically, we're recommending now 128-bit keys, 64-bit keys. This type of data isn't yet going for some of the super secure, secret encryption methods. And as I say, some governments are insisting we go down to 32-bit keys. Okay. Now, digital signatures and equipment codes. One file format I haven't mentioned is PDF. And again, it's quite possible to use secure encrypted PDFs as your data file transfer mechanism. And that gives you an additional level of encryption and decryption that can be very useful. Okay. Now, once you've got that data, again, before you put it in the database, you can reach into your MES, your ERP, grab a few parameters and say, okay, yeah, is this a valid operation? Is it a valid part number? Is it a valid operator? You know, does the MES say we actually built this yet? Has he measured it before we built it? In which case, it's clearly fake data. So you've got this opportunities when the file is there. Once that data is in the database, then we can use a number of statistical methods and comparison methods to existing data to verify the data. You know, we can set up some reasonable limits. If something's 5 millimeters out, clearly they did something wrong. Either they mistyped it when they were adjusting it, or they just didn't clamp the thing down properly. There's loads of reasons, but you might want to reject data if it's outside of a reasonable limit. You might want to run a few statistical things to detect duplicates, changes, and attempted edits. I'll show you some examples of that later. You may want to look at the statistical likelihood of this data being real. You can look at normality checks. You can look at the kurtosis or the skew of the histograms. Now that may be a natural statistical function on this data, but you need a system where you can teach it that, hang on a minute, yes, this slightly skewed histogram is normal, but this slightly skewed histogram over here, that's not normal. We don't expect that. Let's put an alarm on it. Okay, and that brings me down to pattern recognition. There's a number of advanced pattern recognition techniques you can use. We've had fun with using Fourier transforms on data to look at cyclic variation. We found, as I said in yesterday's webinar, we found one company that was actually repeating its data month on month. They'd actually only got 2 batches. They'd measured them some time ago, and every other month they sent the same data in. So we had this repeating cyclic month-on-month pattern, and splitting the data down into the time domain using a Fourier transform showed a double cycle pattern very clearly, and we were able to then find out what was going on. And then closeness to the limit. People, if they are going to cheat, they are not inventive in their cheating. It's something we've discovered over time. If the limit is 1, they will either put 1 or 0.99. If the limit's 0.5, they will put 0.49. Okay, so if you look at the proportion of your data that is very close and just inside the limit, we know what proportion it should be. You know, statistically, that's fairly easy to calculate. And if you suddenly find that double that proportion is very close to the limit, oh, well, we've got a problem. Somebody's adjusting this data. So let's look at that validation and make sure it's true. I've got some examples on the next page here. This big blob of blue data here is real data from a real supplier. This is from a different industry. Nobody gets 100,000 samples in the aerospace industry, but this company had delivered 100,000 parts with this level of variation, and not one of them had been out of tolerance. Statistically, that's virtually impossible. Okay, let's alarm that. As I say, this company here, they've sent the same value in every month for over a year. Again, I should say, these are things we spotted when we first loaded up all the history and installed our system. So this is, as I say, when we got the historical data. Here's another one. Here's an histogram, and it's not badly functioned. It's off center, all the rest of it. Run a normality probability plot and the histogram, and hang on. What's going on here? I've got 2 extreme outliers. I've got a couple at this end as well, but this is probably due for a bit of investigation. What's going on? And as I say, as I load the data, here's an example down the bottom. This is, I don't know if you know the format. This is a DMIS file format here. This is a hexagon DMIS, not a Wenzel DMIS. Okay. But you can see the profile tolerance here is plus minus a millimeter. The person has declared the actual value to be minus 0.99. But we've got the actual XYZs here. They've not been too clever. If you do a bit of 3D maths, which is just Pythagoras, x squared plus y squared plus z squared, you can see that the calculated profile should have been minus 1.2 millimeters, well outside the tolerance. Somebody has been playing with this data, and we need to put a stop to it. Okay, so there's just a few methods you can look at. I'll need to move on because time is running away from us. It's great. You need to consolidate data. Okay. The challenges are you've got all these different measuring devices and data formats. This is where our results analysis and automatic 3D calculation in the background can really help you. You've got distributed data repositories. You know, I've been to several machine companies which have multiple CMM rooms that simply don't talk to each other, even though sometimes they're measuring the same part on different days. Okay, and you've got different coordinate systems, but I'll talk about that later. So there is a need for 3-dimensional recalculation and functional When I say a function, I mean a distance, a flatness, a cylindricity recalculation from the raw data. But once you can do those, you've got a greater depth of data for root cause analysis. Okay, if I've got my final assembly and all my individual components all measured to the same datum in the same format, then I can do some really good root cause analysis. What is causing those final assembly issues? Okay, that allows us to do virtual assembly. And once we trust we can do virtual assembly in the software, we can do virtual adjustment or selective assembly. Okay. We've also got the opportunity there to evaluate process and quality, because we can move our process information, our quality information into the same currency and do a correlation. And that allows us to manage our suppliers in a much better way, because we've got the data. We've got far better data than they have. I've got a few examples here. One example is in the top right here, 5 different suppliers all providing us with data in different formats. We can integrate all that. We can start to see the all up quality of every supplier over time and how they compare to each other. Of course, I've replaced the supplier names with supplier 1 to 5 to protect the innocent or guilty. Okay. Over here, I've got an example from a turbine blade, and we're just here looking at the H section. You can see it's flagged this as orange because we've got a error on contour max at the bottom there. And you can see in the top right, we've got all the process parameters coming from the machine tool controller. Now we can do a bit of recipe management now and say, well, do these temperatures impact the quality? Does the spindle power? Does the motor temperature impact on quality? Any parameters, we can start to control them. Okay, so let's move on. Data storage. Mostly this is an IT department function, okay? But one important thing is keeping the raw data files that have come in. The number of times I've ended up having to go right back through the database, find that raw data file, and prove to somebody that they did something. Okay, so you've got to keep that, but that requires a good data retention policy. It requires good archiving policies. Also, one thing we recommend is that your system, your database, should lock down measurements. Once that data is in that database, there should be no way that a user or even an administrator can adjust that data, the actual measurements. And if they do, you want to track that they did. Okay. Now, it's virtually impossible to stop somebody in IT who's a database guru and has all the company passwords from adjusting things, but the chances of that happening are very, very remote. Okay, and you've still got your raw data files, so you can go back and see what's changed. Security and backup and all of those things, I don't need to mention that really. I put it on there just for completeness. But the one that you do have to think about is allow for obsolescence. I am old enough, just about, to remember one of the first systems I ever worked with used a COBOL database. Now, I actually believe that in some financial systems, COBOL is still being used, but I haven't seen a COBOL database for 15 years. We've recently migrated a whole bunch of data for 5 or 6 different companies from Oracle to SQL Server. How much longer is SQL Server going to be going? How much longer is Oracle going to be going? There are new database formats, methodologies coming along every year, and you have to think about and allow for the obsolescence of your core database. How would you retrieve that data or migrate it when you consider that something might be flying for 20, 30, 40 years, and you've got to keep that data for that length of time? Okay. Now, talk quickly about event tracking. You've got to track data changes, data load events. That's obvious. What about nominal condition changes? If someone just goes in, changes a tolerance, that's significant. You've got to track all those things. So you need a reason why somebody did it, an authorization, the name of the person that did it. And of course, track your data loading events. Was data loaded twice? Was it loaded 3 times? Has somebody been adjusting the raw data files? Let's track those events. And of course, you should track the creation and location of any reports that get created from the database. Okay. Now, this tracking data becomes very large over time. You know, the tracking data can actually amount to more than the data that you're holding. So again, you're going to need an archiving and restoration process for this event tracking data. Otherwise, it's going to slow the rest of your system down. And then I want to talk quickly about report management. We are at the moment favoring printing encrypted PDFs for the standard forms that we create. And we need to manage those form locations and their storage in a data management system in the same database as your data, so that at any time we can recreate a form using the data from the database and compare it to the original. And this may or may not, of course, have required a digital signature. Okay, if it's actually a stage inspection, it's going to require a digital signature. If it's just a piece of background information, maybe it doesn't require a signature. Okay, but again, consider the longevity of these digital formats. You know, PDF has been one of the most stable and reliable digital formats over the last 20 years. But for how much longer will that continue to be the case? But if you've got your raw data files, your original database, you can always reproduce this in whatever format is required. Okay. Dissemination. And then one final slide in this section, and then we'll move on. Yeah. Here's our general principle that we're applying at ATS, and we're finding this works very well these days. And that is, no senior manager should really be looking at an in-depth analysis of an individual feature on an individual part. That's not their role in life. On the other hand, specialists don't want to be burdened with creating big, all-up data reports. So if I'm a senior manager, I'm probably going to be accessing the data on a BI tool, a dashboard. I may get an email of the week's summary or the day's summary. Or I may just want to look at some printed portals organized, or some printed PDFs, sorry, organized in a logical manner. Middle management, again, but I'm going to want a little bit more depth, a little deeper analysis. I'm going to want alarms, I'm going to want and-on boards and alerts for my emails. When I become an engineer, of course, I want, I want access to that raw database. I want to be able to look at what's happened to that pocket over time and track how it's changed, and then maybe draw some conclusions about the way we're producing these parts. And if I'm a specialist, well, I need all the tools to invent entire new ways of analyzing the data that I've got in my raw database. Okay, I've got a few examples here. This is a typical sort of BI tool dashboard for management. Obviously, these are real projects, but I just call them projects 1, 2, and 3. You may want to have something that lets you walk around the shop floor. Again, in this case, it's a real style, but it's fake data. I wouldn't actually show anybody's real data in a presentation. But you may want to have this so you can just walk around on your phone and see how things are tracking. On the other hand, if I'm an engineer, let's start doing some innovative ways of looking at how our data is changing over time. Again, getting down into even more depth, yes, let's start looking at trend charts and statistics, and let's start relating all of our data directly to its three-dimensional position on the CAD drawing, and do that automatically. Okay. So there's our general principle: appropriate reports to different stakeholders and use different media to deliver those reports. Here's just one example of tracking PDF reports here. In this case, we're standardizing the content delivery of the different forms. So we have standard forms. I've got a couple of examples here. I've got a PRID form, and I've got oh gosh, that's a revision A 9102 form. Yes, I realize the standard has gone up now. I think we're revision C. That's quite an old form then. But you get the idea. Is we've got a reporting portal which is customized to your login, so you get to see those reports, those sign-off sheets that actually relate to you. And of course, you may be opening these up in order for you to be digitally signing those forms to approve them. Okay. But as I say, we'll customize that. We'll limit the content to the people who should be using it, but we'll give you easy access to your critical documents. So I need to move on. We didn't have a huge amount of time, and I realize I really have just 10 minutes left. Okay, so here we go. I want to look at some analysis methods that we've been working on recently. As I say, single part analysis, trend analysis, that's bread and butter. Everybody can do that. So let's look at some new stuff. Having said that, I've gone back to basic single sample analysis because we've actually been working with some people recently to look at how we can make this better and faster. One of the things is, once the data's in, you want instant response. I say instant, I mean a few seconds. I'm not talking milliseconds, okay? Our vision of single sample analysis as well is that all of these items should be related directly to a CAD image. So if you've got an issue occurring, you know exactly where it is. Okay, so we always have a live CAD view, and we always show where features are on the part. This example is a turbine blade. Again, it's a real blade. It's just fake data. Okay. What you need to do is be able to set up rules so you automatically find the issues. In this case, the customer asked us to put everything that was in error on a blade onto page 1, and I've got pages 2 and 3 with all the other readings. I think there were actually 6 pages to this report. So errors on page 1, and then we'll do each chord and area onto each own page afterwards. Okay, so at any time, the operator can simply go in, spin the model around, zoom in, and see exactly where problems are occurring. We need to automatically find the issues. We need to automatically evaluate. Now, in this case, we've got working tolerances and concession tolerances. And the rule is, well, it's an orange, it's a rework if we only have working tolerance breaches, because we might be able to get a concession, or we might be able to just rework it. Okay. But I think they also said that if it's more than 10% out on rework, they're actually going to scrap it anyway. So you've got these multiple rules. This also has a SAT check. The reason it's failed the SAT check is reaching into SAP for certain key values and parameters to see if they match. The reason this has failed is because I ran it on my machine and it's not connected to their SAP system. So the failure here is failure to connect. Okay, this one's a scrapper. We've gone out of concession by minus 1.7 millimeters. That's pretty bad on that chord angle. We're not going to be able to recover that. We'll throw this away. Okay, one of the things they have got though is access to previous data. So if this particular blade has been remeasured, I've got access to that data. I can just right click, pick the remeasures, and you can see if our adjustment has actually made a difference and where it's made a difference. Okay, or I can compare this to other blades. You know, are we always out on that chord angle? Is that a systemic fault? In which case, let's talk with the engineering and get it fixed. Okay, so single sample analysis, but let's put a bit of logic and learning into that. Here's another toy that we're working with. I really like this one. The example here would be the attachment points of a nose cone to an aircraft. Okay, now if all those holes are 0.1 of a millimeter to the left, the nose cone is still going to fit on. All the locating pins and lock pins are going to go in, no problem. So if the whole pattern is 0.1 of a millimeter to the left, no problem. But if some of those holes are 0.1 of a millimeter to the left, some of them 0.2 of a millimeter to the left, then we're going to struggle to drop this in and have it fit very neatly. Yeah. And if the whole pattern is too far out, then of course we're going to get gaps around the side, or the thing will sit skew. So we need to be able to track that. So what we've been working on is allowing people to define a group of holes that should form a pattern. Once we've done that, we can calculate the spread and the center of the pattern. So we can apply tolerances to the center position of the pattern, the spread of the pattern, and of course any individual feature. Once we've done that, we can just let the system track and alarm that automatically. And we can look for trends, you know, as we go through time. Are these patterns moving to the left? Are they moving to the right? Are they gaining spread? I've got an example here. Obviously, again, we've changed the CAD model to protect, in this case, the guilty. There's far too much spread on this pattern. So if we were to try and fit the nose onto this body, there's every likelihood that we might start putting the pins in and find that some would need to be re-drilled and wouldn't fit properly. Okay, very useful. Part-to-part matching. Again, I've had to replace the CAD. I can't really show you the CAD of this aircraft. So we've got an aircraft fuselage and an aircraft wing made out of Lego. And I apologize for that, but for some reason they wouldn't let us have the CAD. I don't know why. But in this case, we've got a wing and a fuselage that are 1,000 miles apart. One scanned using a Leica laser scanner, the other one using a Faro. We don't care. We've been able to convert all that data to a single database. But these two things were actually measured to two different datum schemes. That is, the fuselage, we locked onto the jig fittings. The wing, we also locked onto their jig fittings. But there's no guarantee those jigs are in any way aligned to each other. They're 1,000 miles apart. But we know when we put this together that this pin is going in this slot. This pin is going in this slot. What we can do in the software is create that as a new datum scheme, move all the measurements to the common datum scheme. And at this point, we can now calculate the actual likely gap. Now, obviously, in this case, we've calculated the gap between the wing, and we've also calculated the flushness or the contour. Okay, so we've done two jobs there. One of the nice things is, of course, if you've got 5 wings going down the line and 5 fuselages, we can then measure them all And we can say, oh yeah, actually wing 3 fits best on fuselage 2. Wing 5 fits onto fuselage 3 with the least gap. The other thing we can do in the software is we can play with pin 1. Let's move it a millimeter. What happens to our gap and flush? It's far easier to move a pin or a locator while the thing's still in the jig than it is to ferry it 1,000 miles, find the darn thing doesn't fit, and then have to start clobbering things with big hammers. Not that you would actually do that, but actually physically move it once you get into position. Okay, so virtual fit, part-to-part matching, and the ability to stack these things. If I if I take this interface, maybe I then have another part that locates onto this interface, and I have 4 or 5 parts that all have to be assembled together. So the ability to look at matching 4 or 5 parts into one assembly and calculating the gaps before we start shipping these parts. Correlation, how am I doing for time there? I think we need to really get a move on. I've only got 2 more slides, so I'll talk about this. 3 reasons for using correlation analysis in aerospace. The first one is aerospace, we often over measure. I remember one CMM operator crying out at me. He was measuring 3,000 points on a part, and he knew darn well that 1,000 of those points were just not needed. Run a correlation analysis of every point to every other point. You'll very quickly find you can reduce that measuring plan. Okay, you can run a correlation between one part and another part, maybe between an individual component and an assembly. You may well find that an issue on one part of a component always reflects in the assembly. And remember, it may have a seesaw effect. It may have a reverse impact. So a high on one component may push another part of a component, of an assembly, down. And then, of course, traditionally, we've used correlation to correlate process parameters to feature quality. That allows us to optimize the process. Can I turn up the feed rate by 10% and still get good quality? Maybe. Does it matter if the spindle vibration goes above this certain level? Is that going to affect surface finish? Well, let's run a correlation study and see if historically it has, because we've got all this data. One of the problems is there are loads of tools out there that let you do this, but they're not that easy to set up. If I had to run a correlation analysis in, say, Minitab of 500 points to 500 other points, it will take some time, let's put it that way, because you have to do each pair individually. So again, we've had to develop techniques that allow us to do 1 million correlations, automatically identify those strong links, and then give the sort of reports I've got here, which is actually from a hood on a vehicle, on a car, I realize, just shows the detail on the strong correlations. And in this case, why are we measuring these 2 features down the edge of this hood when there's such a strong correlation? Okay, now here's a new opportunity. Once we know we've got a strong correlation, let's register that in the database. Let's allow this database to do a bit of learning. So if you have a problem on a assembly, you can immediately say, okay, we know there's a strong correlation between this problem and issues on these components. So let's pull all the data for those components and see what's going on. So let's allow our computer system to learn what influences what, and then pull that back and save our engineers a ton of time. Okay. Finally, and this is my last sample, and I do apologize for going a little bit over now. Process analysis. This is one of the ways we can get past this low sample count in the aerospace industry. For sure, this Makino I've got here produces 2 rib 5s a week. It might produce a couple of brackets a week. It might produce 4 little mounting blocks a week. But if you look, this thing's running 24/7. We're sweating this asset. So if you were to look at what this machine has done during the week, you've got a lot of data to do some statistical analysis on. So again, we've developed this method where we can find all the components produced on an individual process or machine within a time period. We can then group those features by their cardinal direction so that we know these features, these holes, these surfaces operate in the X direction, these operate in the Y, these operate in the Z. And then we can look at the mean offset and the amount of variation in each of those components. The example I've got here, I actually found 45 components that had gone through this Makino within this, I think it was a 4 or 5 day period. Now, if you look at this X deviation graph, it's pretty stable. However, I think we had one setting error, maybe a tool breakage, I don't know. Something happened to one component here. We can forget about that one, I think. But generally, the machine is pretty stable. I've asked the system to predict ahead. You can see there's actually an angled trend line here. And it's actually predicting that in 194 components, if this situation carries on, we're going to hit the upper tolerance that we've set for the X deviation. Okay. Now, not every component's the same. Some components are going to wear the machine more than others. We appreciate that, but it's an indication of how much more life you've got. Okay, and then look at the Z here. It's already over this tolerance. This thing is consistently producing parts where the Z is out. Now, obviously what we've done is set these deviations to be well within the acceptable tolerances on the component, okay? Because we want to control this machine to such a tight extent that it always produces good stuff. All these components probably passed inspection, but we're looking down at, I think, yes, maybe 100 microns as our target for this error. And as you can see, it's probably time here to get the maintenance department in and adjust that axis. If I see a spread error, then of course I'm seeing looseness, slackness, or just wear and tear on that axis. And again, time to call maintenance. And what you need is an automated event that finds these errors and maybe automatically pushes a message into the maintenance management system. And just for completeness, because I like to bring lots of data together to give me an overview of this Makino, I've dragged in the spindle vibration measured on the accelerometer over the same time period. Of course, I deliberately picked one here where an event had occurred a couple of days ago, and the spindle is obviously due for a good check over. Let's see why the spindle vibration has gone up so much. Okay, so as I say, you can easily get over, well, not easily, you can get over this lack of data. That's it, because I realize I'm a couple of minutes over here. We didn't discuss some of the stuff. I touched on selective manufacturing. We haven't talked about how we're working with BI tools. We haven't talked about the whole other side of data gathering, which is looking at checklists and looking at observations and pass fails there, and then integrating that data with your measurement data. Okay, that's a whole other subject for another webinar. But if I say something that sounds interesting, and I love to play with dimensional data and see if we can find these sorts of issues and patterns, please get in touch with us. I hope I haven't droned on for too long and that I have given you some ideas for how you could apply some better methods in your own factory. So thanks for listening in, and I'll hand back. Sandeep still there?
Thanks, Ed. And thanks a lot, gentlemen. Ed, we do have a couple of questions over here.
Okay, yeah.
One is, a lot of companies are providing certificate of conformity, that is COC,
Yes.
for the items supplied by the OEMs. However, is there any procedure for checking the veracity of that COC?
So if they just provide you with a certificate, just a piece of paper, or even a digital certificate, there's things you can look at. You know, you can check a lot of the information that's in there. If it's a PDF, we can extract that information from the PDF, compare it to your MES. But without the raw data, it's difficult to verify the certificate of conformity. So for me, I always ask suppliers to give me the raw data with the certificate. Okay, if I've got the raw data, I can examine the raw data, or I can get the system to examine the raw data and verify the certificate. But if they just give you a piece of paper, it is difficult, yeah. But if you've got the raw data, you can certainly verify that they did it. And then, of course, you've got to verify that the raw data that they gave you is an accurate representation. Yes, you can do it. The raw data is the way to go. Okay. And what we did at one company where we suspected the certificates were out was we actually, just for a couple of weeks, we put in a inspection on arrival. So we actually inspected critical features when the components arrived. And of course, we found a discrepancy in this case because we already had suspicions. But yeah, raw data is the way to go, I would say. And if you don't trust the raw data, you're going to have to get an inspection on arrival. Okay.
Yeah. And there is another question. Can we use CM4D for the automotive parts?
For automotive parts?
Yes.
Oh, absolutely. So obviously, I was asked to give a presentation here aimed at the aerospace industry, and they chose me to do the presentation because I worked in that industry. But I would say 80% of CM4D usage is in the automotive sector. So we have, for example, Ford Motors. Every Ford factory pushes all its dimensional data into CM4D. We're working with a lot of other big names. Volvo's a big name. Honda's we work with Nissan. I'm about to do an installation at Lotus Cars in the UK, which is a tiny manufacturer, but that's going to be great fun. I love their cars. So yeah, definitely automotive is actually our forte.
Yeah, I think on a broader level, CM4D can also be used in most of the discrete industries, right?
Yes, I mean, as I say, we were asked to give a aerospace focus. You know, anything you can measure that is a variable, CM4D is very good at analyzing that data. And if you've got variation, dimensional variation, and a CAD based system, that's where we're incredibly strong. You know?
Yeah, the last question, how are forms such as concession stored?
Yes, okay, so yeah, because obviously in aerospace, you're likely to get concessions floating around. So two things, first of all, digitally, there's two things we can do, sorry. Digitally, we can scan that form in. We can then put that scanned image into a secure location, and we can register in the database exactly where that is. Now that means that any report that you see can automatically recall the correct scan, okay? Because we have its location, we know the file type, we can bring it back. Okay, there's another thing you could do as well. If that concession is in a filing cabinet somewhere, you can also put that information into the database and recall that at any time. Personally, I like to scan them in because bits of paper tend to get lost. Okay, so yeah, scan them in, put that location in the database, allow the system to recall it.
Yeah, I think that's all, Ed.
Okay, thanks very much.
Yeah, thanks a lot, gentlemen, for joining the session and taking out your time.
Yeah.
And if you have any questions, then you can write us back, and we will be happy to assist you with your queries. And thanks a lot for your time, and enjoy your rest of the day now. Thank you.
Okay, thank you very much, and goodbye.